Hi, my name is Jim, and today's topic is Introduction to Filters, and this will be part one, and it's basically a review of AC circuits, plus we're going to be introducing a different form and a very brief introduction to something called Laplace transforms, which is very helpful tool, especially in circuits where you can replace calculus operations by algebra. So we'll start out with filters, and the purpose of a filter is to be able to eliminate or pass a frequency that is desired. And in general we have four types. One is a low pass, and the purpose is to remove high frequencies. And a good example of that would be say an anti-aliasing filter for a to D converter. Low pass to if you're making a signal to noise measurement, say for audio, you don't really need to measure noise content above 15 kilohertz. So if you eliminate that, when you make your actual test, it'll give you a more definitive answer of the true value of the signal to noise ratio that people can actually hear. We have bandpass filters. We select frequencies with that. You do not tune in a radio without a bandpass filter. It has to select a frequency of interest. And then a band reject filter, which removes a band of frequencies. For example, in an audio system, if you have hum, because audio lines from the microphone to the amplifier are, say, in the ceiling with Romex wire carrying 60 hertz commercial power, you might want to notch out a portion of the low frequency to attenuate the hum component. So we have two different general types, an inductor capacitor circuit LC versus a resistor capacitor RC. And we're going to be talking about today principally first order filters, which means we have a single time constant, that is in R and an L, or in R and a C. But this applies to any order of filters. And by order I mean that, for example, in a low pass filter with an R and a C, our ultimate roll-off is negative 20 dB per decade. And if we have two R's and two C's connected properly, that would be negative 40 dB per decade. So that would be an example of a second order filter. So for using an inductor or a capacitor here, what we have is LC circuits are good in RF applications, where operational amplifiers would be hard pressed to maybe operate at some of the frequencies that we're going to be seeing, or expensive. And inductors are, and this is a good thing, and a kind of bad thing is inductors are relatively large compared to capacitors and resistors, so that would take up more printed circuit board real estate. And inductors are subject to ingress. Now what that means is it's in some form a coil of wire, and another name for that is an antenna. So ingress means that external signals are being received by the inductor, and what that shows up as is noise for the signal of interest. Inductors typically cost more. That's usually a factor. And there's fewer parts for a given order of a filter. So that may be of interest, and that's a positive. And then what we have here is they're passive, so you don't need to apply any power to a passive circuit. That's a plus. And there's no lower noise. Now we have to be a little bit careful when I say that, because this is shielded, and the noise I'm talking about is Johnson noise, white noise, and what that's proportional to is the bandwidth of the circuit, the temperature, and Boltzmann's constant. So the only noise that's going to be introduced by an inductor is a winding resistance. Inductors, meaning the inductive component, or capacitors, do not introduce noise, Johnson noise. So in an RC circuit, it's good for lower frequencies, certainly smaller because we can use surface mount stuff. It's less subject to ingress. Of course, we may have to do some shielding in addition to make sure if it's critical or the signals are really low in level. That's lower cost. There's typically more parts, and it's an active circuit, and that means it requires power. That's kind of a disadvantage. And typically more noise, and that not only includes that of the resistors, but the operational amplifier, if one is used in the circuit, would be adding to the noise. Now when we look at low-pass filters, it doesn't have to be anything special, and what I'm holding here is a USB type A to mini, and we see this little lump in the cable here, and you see these a lot on computer cords and monitors and so forth, and this is a low-pass filter. And what its purpose is to keep any high frequencies from the device that we plugged in here, say an MP3 player, from using the rest of the cord as an antenna. So anytime you see a lump in a wire, so to speak, it's a low-pass filter. So we're going to be talking about first-order filters. As described before, they simply have one energy storage element, an L or a C, and we have the concept of a critical frequency, and in the examples we're going to be using, that's going to be 1592 Hertz, 1.592 kilohertz, and that is defined for our network here is the point where the output of the filter drops by 70.7%, or in the log domain that would be negative 3 dB, negative 3.01 dB, but we'll just call that negative 3 dB. And what we need to note is that's down on the curve a little bit. And this is in fact the corner frequency, and then a little bit later we'll describe that from the standpoint of revisiting Bode plots, which are very important in filters. So let's talk about values a little bit. And what we're going to do here is try to find the value of a capacitor. So we're given the frequency, and I'm going to select an R. So the value that you're going to select would have to do with the impedance in general of what you're working with. Now, making R too low means that the electronics associated with it may have a difficult time in driving it. And making the impedance too high means it's subject to electrostatic and electromagnetic interference, principally electrostatic. So we try to search for the sweet spot here, and it's sort of relative. It, again, depends upon the circuits we're working with. In some cases of a matched filter, the input impedance and the output impedance would have to be 50 ohms, and that would require some special additional design steps. So to find that critical frequency is what we do is we set the magnitude of the capacitive reactance, and I'm using absolute value symbols here to specify magnitude. So we're not dealing with any angles. We set that equal to R, and what this is going to do is basically produce a, I want to say 50% voltage divider, and this would be the equation that we end up with, 1 over 2 pi Fc, which is the equation for capacitive reactance, is equal to R, and then all we have to do is solve for C. So here I'm multiplying both sides by 2 pi Fc, and then what I want to do is to isolate C, and well, first I isolated F here. This is typically what we do is we look for the critical frequency. So I put that down as a first step, and you should be familiar with doing that. So wiggling this around here, we end up with our F critical, and in putting that into context with the critical frequency on the left side of the equal sign, it equals 1 over 2 pi RC, which should be somewhat familiar. Now, throughout this, we're going to be using the critical frequency, and in addition, it's going to be using F sub 0. Now, these are interchangeable. It's just that as we move into filters, F sub 0 and contrarily omega sub 0 is a more commonly used. So as we change the values here, it means the same thing. So not to be concerned about that. It's just sometimes this usage is more prevalent, and other times the sub 0 is more prevalent. So if we want to find the C value, all we do is take the same equation here and solve for C, and that equals 1 over 2 pi RF, and using the values here, that comes out to be 99.97 nanofarads. So I'm going to round that up to 100 nanofarads, and realistically this part is going to have tolerances which will swamp the difference between the theoretical value and the actual value by, I don't know, typically 5% if we're lucky. 10% would be more probable. So here we have our circuit, and one of the things we have to be very careful of is to take note of what the driving impedance is. Now, for example, a generator typically has a 50 ohm output, so our resistor in series here would really be 1050 ohms, and that's going to affect to some degree the output of this, and considering that to be insignificant. If this is driven by an operational amplifier whose output impedance is really, really low because of the feedback is just considered to be 0 ohms. So if we had a source here, say with a 10K output impedance, which would be typical for audio, that 10K would be adding to the 1K, and our critical frequency would be completely different. So what we would have to do in that case would be take that 10K in effect and find a different value of C that would give us the desired corner frequency that we want. So you always have to keep that in mind. And the second thing is we look at V out here is unloaded. So put a meter out here, that's fine, it's a megohm, but whatever. It's not going to hurt anything because these impedance values are relatively low compared to the loading. And theoretically this would be in, our load would be infinite. Now if we're coupling this into an op-amp in the non-inverting mode, it could be very, very high. We would have to provide a resistor to ground out here for bias currents, but that could be, you know, in the hundreds of thousands of ohms. So let's take a look at the way this behaves, and this is kind of important, and I'm not going to use any limits here, but this is where it lives for proof. And a low-pass filter at DC means that the capacitor looks like an open circuit. Now to make sense out of that, and here we see the capacitive reactance, and I have it goes to infinity, is if we look at the equation for capacitive reactance, we see that in the denominator the frequency is located, and as the frequency increases, the capacitive reactance decreases. So if F goes really, really high and approaches infinity, X sub C goes very, very low and approaches 0. And the curve for that real quickly for X sub C would be like this. We have two asymptotes here. This would be F, and this would be X sub C. So F will bring X sub C towards 0, and if we go to DC, which is often referred to as 0 hertz, X sub C approaches infinity. So capacitors are good for blocking DC, as you see on your scopes when you have direct couple, meaning that DC will be displayed on the scope, or AC couple means that there's a capacitor in series with the scope to block the DC, and it's based on this principle here. So let's see here. So at low frequencies, since our capacitor looks like an open circuit, V out is going to be equal to V in, and that assumes, of course, that we have an infinite resistance loading out here where we're not having any current flow through the 1K resistor. Now at high frequencies, what we have is the frequency goes to infinity, X sub C goes to 0, as we see here. And what that looks like is the capacitor appears in the circuit as a short. And that means that the output voltage under that circumstance would be 0 volts, and all of Vn would appear across the resistor. Now, what we would say about that in the language of Laplace is that we have a 0 at F equals infinity, which is a 0 transmission. Nothing's going to go through it, so that's called a 0. Okay, let's do some calculations here, and what we're setting up for is a different method of solving this, very similar, but just as a refresher here, we're going to use voltage divider to do this, and I'm going to let my input voltage be 3 volts, and I'm going to let my frequency of interest be 2 kilohertz in this case, and we have the same circuit values we had before, 1K and 100 nanofarad, V in and V out labeled as such. And I'm going to apply the voltage divider principle here, Vin times the ratio of the impedance of the capacitor divided by the total impedance. And then populating that with the symbols here, we have negative J X sub C in the numerator, and in the denominator we have the total, which would be this added to this. And when I say added to, it's not a direct addition. And then to do this, we'll have to find out what the capacitive reactance is at 2 kilohertz. And that turns out to be 796 ohms. Now notice that there's no angle with this. And the reason is because I'm designating this a capacitive reactance. That's the words I'm using. So those words mean that the angle is going to be 90 degrees. It's embedded in the term. The impedance of a capacitor, on the other hand, needs to have that angle displayed. So working through this is what we see in the numerator. It's the guy we want is across the capacitor is our 796, this time displayed with negative 90 degrees ohms. And in the denominator we have the total impedance, and what we have to do is take the square root of the sum of the squares, and the angle on this is going to be the inverse tangent of our 796 divided by our 1K, the real component here. So going through this, what we end up with in the denominator is 1278 for the magnitude and a negative 38.52 for the angle. And then if we divide 796 by 1298, that'll give us the magnitude, 1.87. And we subtract the angle in the denominator from the angle in the numerator, so this is going to be negative 90 degrees minus a negative 38.52. So that'll give us 1.87 at negative 51.48 degrees volts. And once again, if we were to plot that, in here we would have the 51.48. And since I don't have a negative here because I'm showing this in a graph as extending into quad 4, and my 3 volts here would be the input voltage, and then that would break down into real and imaginary. It'd be this guy here, and that would be our 1.87 output. So 3 volts is shown as a phasor, and then this would be the output phasor. Now to plot this, my expectation is that you wouldn't guess at the angle and you wouldn't guess at the magnitude. You would actually determine the value of the real output, and that would simply be using the cosine operator, and the value of the imaginary output, which would be using the sine operator, and then doing the dotted line thing and ending up with a very precise point here for the voltage of the output. So the transfer function is another way of saying this, and this is just a ratio of V out over V in, and you can kind of think of this as a box, and you're going to send a signal into it, you're going to get a signal out of it, and how does that box transform the signal? What does it do to it? So setting this up in notation is just the output voltage divided by the input voltage, and note that this is dimensionless based upon the ratio of what we had before, and then dividing this out is what we get is our 0.602, and that would be this divided by this, so that's pretty good, and it would have an angle of our negative 1.48 degrees. So putting that into English, if we took our output, we wanted to find output voltage, we would take our input and multiply it by this term, the transfer function, is it would give us the same output voltage as we got by using voltage divider. This here is also dimensionless because we have ohms over ohms, and this just is the ratio of this guy over this guy at that angle. So that would be the transfer function of our network here. And the network, I don't have the schematic up, but it would simply be the resistor in connect to the capacitor to ground. So that's not too bad. It's called a transfer function. And in our case, we would evaluate that again with 2 kilohertz. And again, both quantities are dimensionless. So let's do something useful here. And we're going to take our little filter circuit and we're going to connect it into a real circuit. And what the concern here is the driving impedance and the load impedance. And what I've done here is connected this into a non-inverting op-amp, and I'm providing a bias path to ground of 10K, and a lot of audio processing consoles and so forth use 10K as a standard impedance. And I've got a little open there kind of to show that. But so what effectively is going on here is I'm going to have 10K in parallel with the capacitor, 100 nanofarads, and I need to know if that's going to change the critical frequency or not. So I'm going to set up a circuit for an example using the output impedance of the op-amp is 0 ohms, so I don't have to be concerned about the driving impedance. And again, Vin is going to be 3 volts, and I want my critical frequency to be 1.592 kilohertz, 1592 hertz, same as before. So in drawing the schematic with the load on it, as I can see my 10K in parallel with C. And what I want to do then is to find out for voltage divider what is going to be the output voltage at extremely low frequencies. Okay, what we know about that is at low frequencies the capacitor looks like an open, so I've left this open, and now I'm simply dividing with a 1K and 10K in voltage divider, and I see that that ratio becomes 0.909, which means the output voltage at really low frequencies is going to be 2.72 volts repeat. So I'm not going to have my 3 volts output as I did before when I was unloaded. Now we have to find the value of C here, and we're dealing with a different resistive component, 909 ohms compared to 1K. So that's going to change things. And then to solve this is what we have to do is, well, one way at least, is to bring in the Thevenin equivalent circuit. And what we're going to do is disconnect the component of interest, which is the capacitor, and look into this. Now we already know what VTH is, and that's him. And I did that without mentioning Thevenin, but essentially that would be part of this operation. And what I want to find here is RTH. So looking in here, we have to take into account the impedance of our driving source, and this is a voltage divider or op-amp. And what we know about that is that a voltage source's internal impedance is 0 ohms. A current source internal impedance is infinity. And that's absolutely imperative that you know that. So if this is 0 ohms, I can replace it with a short circuit, and the 2 dots are where I unplug the source resistance and put that in. And looking into this is what I see is that 1K is in parallel with 10K, which gives 909 ohms is our total resistance for our circuit. So building the model for that, I'm now going to have 909 ohms with the capacitor C. And as you can probably realize, if the resistance is going to go down, the capacitor has to go up. So to find C here is all we have to do is take a look at our equation here for finding the critical frequency, 1 over 2 pi RC, and then wiggle that around a bit to find out what C is, and that comes out to be 110 nanofarads, which is a little bit higher than the unloaded value of 100 nanofarads that we predicted. So this is a fairly straightforward calculation, and it's based on real-world values here, because typically you're not going to have this being fed into some infinite ohm thing unless it truly is an op-amp. And we could make, if we weren't dealing with the audio impedance level of 10K, we could make this say 100K and just simply not worry about it. But we do have to have a path back to ground in this case. And also note that any DC offset here is going to drastically upset this op amp. So there's no DC blocking. And we could fix that if we wanted to by putting a really large value of C in here, which wouldn't affect the frequency, but it would block DC. So there's some nuances in here we have to be a little bit careful of. And one of the things that I think will be helpful is that we're starting out here with this value, and this has a time constant, tau equals R times C, and down here we have a time constant, tau equals R times C, and they're the same. 909 ohms times 110 nanofarads is going to be the same as 1K times 100 nanofarads. So from the standpoint of a sanity check, just keep that in mind with regard to tau. It's certainly easy enough to remember R times C for an RC circuit and L divided by R for an inductive circuit. So this is a practical implementation of a filter in a real circuit. Now to take a little look at this, and this is the same circuit as we had before, let's look at some graphs here and it'll kind of make things a little bit more straightforward. Our VIN is 3.3 volts, and what we see is a maximum output voltage because of the voltage divider with the 1K and the 10K. It's going to be our 2.72 volts. We're going to be reaching our critical frequency here at 1.592 kilohertz. And there I've got the dot, and this is again 70.7%, negative 3 dB point, and I've projected that up here just to show where the corner would be if we were going to draw a Bode plot, and we'll do that a little bit later. Now the phase response at low frequencies, basically where the C is not even in the circuit, is going to be 0 degrees, because all we're dealing with here is a resistor, which is not going to color the phase at all. And then as the frequency increases, the capacitor's effect is felt more by the circuit as the capacitive reactance drop, and we move here to a negative 90 degrees. And these are both asymptotes. The phase plot is asymptotes also. So that kind of gives us a graphic of what we're doing in our practical circuit. So let's go back here a little bit and talk about the J operator, and we're going to get into a different way of determining the critical frequency here. And there's a whole book written on J operators and what they mean in different contexts, and I'm not comfortable with the square root of a -1, but if I look at it from the geometric standpoint, it becomes very, very clear to me as what that means. So we're going to start out here with a value of 3, and that can be 3 ohms, we'll say. And if we multiply it by J, all we're going to do is rotate that 90 degrees, and then we're going to specify that value as J3. So what we can say here is when we multiply J's together, we're going to be moving counterclockwise 90 degrees, and if we were to divide them, we'd be moving clockwise 90 degrees. So we would express this then as 3 times J, or 3J. So 90 degree rotation per J isn't bad. Now let's do that again. Let's say we have J times J, and we'll let this guy be 3 again here. So J times J is going to be J squared. So the first J brings us up to the J axis, and the second J brings us down to the negative real axis. So what we know then is that J squared is equal to -1, and we can see this geometrically as it moves over to the other side of the origin on the real axis. So multiplying J squared times 3 would be resulting in a -3 on the negative real axis. Okay, let's back up to here, and our F critical now is I'm equating that to F0 just as a reminder that they're basically the same thing. Again, absolute value of X equals R, and then solving for this, F0 is going to be equal to 1 over 2 pi RC as it was before. Now what we're going to do is express this as omega 0, and this is the language of filters. It's not in frequency. It's typically in omega. Audio guys like frequency, but everybody else is omega 0. So all we have to do in this case is to take our guy here and divide both sides, or multiply both sides rather, by 2 pi. And what we get on the left side of the equal sign is 2 pi f, that's omega. Or we could write that as omega 0 equals 1 over RC. All fixed. So remember that omega is simply 2 pi f. And this is the number of radians per second. And the 2 pi is 6.28 approximately. So there's no magic there. One book called it the circular frequency, and most textbooks call it the radian frequency. So when we see omega here, it's just another way of expressing frequency. Now, we're going to get into a very light introduction to Laplace transforms, and this becomes very useful later. And you're familiar with transforms. For example, using FFT on a scope, you transform from the time domain into the frequency domain, and you can see the frequency components that make up, say, a square wave very easily, that you could absolutely not see in a time domain. Likewise, we transferred from the linear domain into the log domain. And in the log domain, adding is the same as multiplying the linear domain, and subtracting is the same as dividing in the linear domain. And I might argue that adding and subtracting is easier than multiplying and dividing. And there's also some benefits with exponentiation and so forth. So getting into the log domain can make those types of operations a little simpler. So moving into the Laplace domain means that we have differentiation, which is, in calculus speak, determining the rate of change, and integration, which is meaning summation, the area under a curve, for example, are transformed into algebraic manipulations. So once we do the transform, integrating and differentiating simply becomes algebra. And then when we're done with that, we have to transform it from the Laplace domain back into the time domain. So that's pretty cool stuff. It takes a lot of work out of a lot of circuit calculations. And in the Laplace domain is we're introducing a new variable called a complex variable S, and it has 2 components, tau and j omega, and this is basically the real component, the imaginary component. And we can say also, and this is the second definition for S, is it simply equals j omega. Now, what we're going to do here is let it equal j omega and substitute this in so we kind of get comfortable with using the complex variable S. So we're going to revisit our problem again, and V out over V in is our negative JXC over R minus JXC again, just like it was before. And here I've expanded that into the actual capacitive reactance equations for the numerator and denominator. And then what I'm going to do is kind of clean this up a little bit. I'm going to multiply this here equation by its inverse, omega c over negative j. And I have to do both the denominator and the numerator so I don't change the value. So what I want to do is kind of clean out the numerator here. And when I do that is I get 1. So omega c divided by negative j times this would give 1. And then in the denominator we would be picking up this term, omega rc over negative j plus 1. And this would be the plus 1 here. So writing that in standard form is we would have 1 over omega rc divided by negative j. Now, negative j in the denominator, although it's mathematically correct, is not a desired form. So I'm going to take this term here and multiply it by 1, which isn't going to change anything, which is negative j over negative j. So when I do that, in the denominator I get positive j squared. And what we know about that is j squared is equal to negative 1. So I'm writing that there. And in the numerator now we have our negative j operator sitting in front of omega RC. So, in taking care of combining this, if we come back to here, is what we see is we have a negative divided by a negative, which gives us kind of the answer what we're searching for is the ratio of V out over V in is equal to 1 divided by plus j omega RC. So that's getting set up for the form that we want to use here. And then, if we elect to substitute this, and we'll be expanding on this shortly. So this is a busy page, I understand that, but we'll break it down a little bit. Omega 0 is equal to 1 over RC, as we see right up here. And if we elect to, taking this RC, we can replace that by omega 0 in the denominator, leaving us in the numerator j omega. So this form has 1 divided by 1 plus j omega divided by our circuit constant for the critical frequency, omega 0. Now let me go through that again. Omega 0 is equal to 1 over RC. So we're going to replace RC with 1 over omega 0. And the numerator would stay the same. Here, j omega would remain in the numerator. So that's the form we would get. And that's a very common form for determining the transfer functions of single time constant circuits. So what you kind of need to be comfortable with this form, and if you're going on in your education in 2 plus 2, you're going to be seeing that a lot. And it's just really a wiggled around voltage divider form, really. So let's revisit the problem yet again, and this time we're going to be using the complex variable S, and as we said before, that equals j omega. And if we substitute this in here, is what we see is we have 1 over SC. So S is 2 pi f, so our numerator and denominator look like this. And this is basically equivalent to the voltage divider we had before. And then to clean things up a bit, we're going to multiply this by 1, which is complex variable S times C, numerator and denominator, and that gives us this form here. So all is well. Got a little interruption there. The camera stops at 30 minutes, so we're talking about this guy, our complex variable, and what we need to do is just come down and remember that in our case here, S is equal to j omega, and omega 0 is equal to 1 divided by RC. We end up with a form which is 1 over 1 plus S over omega 0, and that's simply manipulating this guy a little bit, pulling the RC and substituting that with this guy right here in the denominator, since we have to take the reciprocal of both sides of this, since RC is in the, per se, the numerator of the denominator. But anyway, that gives us omega 0 down here. So this is the same as that, and we end up with a form that is 1 over j omega, which is going to represent the radian frequency of our desired 2 kilohertz divided by the radian frequency of our corner. So that's kind of where that ends up. And let's work a few examples on this just to kind of keep this straight. Example 1, we're going to let R equal 1K and C equal 100 nanofarad. And this is going to be our circuit here, and we're going to solve this the same as we did before using voltage divider. We have the X sub C is 796 of negative 90, and we're setting this up as voltage divider here. We're taking the output voltage across the capacitor, and this is the total impedance of the circuit there. And do note that we have to deal with this because it has an imaginary in it, by taking the root of the sum of the squares, and in so doing, what we end up with a denominator in the circuit is 1.28K, sitting at a negative 38.51 degrees. So now it's just a matter of dividing the denominator into the numerator and then what we get from that would be 621 at a negative 51.49 degrees millivolts. So we're subtracting negative 38.51 from negative 90 to get that angle. So if we elected to display this as a circuit transform, we would just take the output voltage divided by the input voltage and state that that's equal to 0.621 at an angle of negative 51.49 degrees, and that would be at 2 kilohertz. So that would be how that would change the circuit. So that's our first example. And our next example here is we're going to be using this form, and what we have to recall is that the critical frequency F would be equal to 1 divided by 2 pi RC, and then multiplying both sides by 2 pi would pull this out to here, and this is equal to omega 0. So omega 0 equals 1 over RC again, and if we work that through, we find out that that is 10k rads per second. Now a radian is there's 6.28 rads per unit circle, and just think of that as that many pieces of pi times the frequency. So we have 10,000 radians per second, and that would be for our critical frequency. So if we go to populate this in the numerator, we have j omega, and that's going to be 2 pi times 2k. That's what we want to find out as far as our circuit response divided by 10k rads per second, which relates to our omega 0, our critical frequency. And then working that out, what we end up with is a simple equation, 1 divided by a real 1 and an imaginary j, 1.275. And if we were to plot that, and this would not be in ohms or any units like that, we would have 1 as a real and j, 1.257 as an imaginary. So all we have to do to find the magnitude of this is standard stuff, the root of the sum of the squares. So we have to square everything here. So 1 squared does 1, and 1 squared is 1, and it gives us this guy here. And adding these together, we get 1 divided by 1.606. So working that out, what that gives us is 623 millivolts, which is the same as what we got before. Now the angle is going to be the negative tangent of the imaginary over the real, and that comes out to be negative 51.50, same as before. Now you may or may not have seen negative tangent before. The standard form is, if you have an equation like this, is you divide the magnitudes and you subtract the angle in the denominator from that in the numerator. And if you have a 1 up here, I typically will put a 0 after it and follow the same rules. Subtract negative 20 degrees in this quickie example from 0, which would give me positive 20 degrees. Now, if you don't do that with putting the 0 here, all you do is put negative tangent, and it gives you exactly the same thing. So no magic about this. It's just a different way of doing this kind of thing when you're dealing with a reciprocal, and in the denominator there's a polar value. So that's good, and let's take a look at another way here. Example 3. And again, I've worked out FO just for the heck of it again and found that to be 1.592 kilohertz. And I'm going to now represent this, instead of omega, as a frequency. So, same form as you've seen before when we talked about omega, but in the numerator we have minus JF, and that's going to be our frequency of interest, which is 2K. And in the denominator we have F sub 0, which is our critical frequency, 1.592K. So again, taking care of business in the denominator here, we've got to take the root of the sum of the squares, and we have to be careful that we do the division before we square it. So I put those in parentheses just to make sure that I don't make a mistake with the order of operations. And that gives us 1.256 squared. Taking a root of that is 1 over 1.6 0.61, and that equals 0.622, and that should sound familiar. So our V out from the standpoint of the magnitude is going to be equal to V in, and that's going to be 1 volt times the transfer for the magnitude, which is 0.622, which gives us, as we should expect, 622 millivolts. The angle again is going to be the inverse tangent of the imaginary over the real, which is negative 51.47 degrees again. So the total answer here is going to be 622 at negative 51.47 degrees millivolts. So we've got 3 basic ways of doing this. One of them is standard voltage divider, and the other is using a simplified formula like this, except this is going to be negative j omega in the numerator and omega 0 in the denominator. And the third is to actually use the frequencies in this to figure out what our output voltage would be, or what the transfer function would be containing these 2 values here. So this is probably, if you look at it, a little bit easier than doing the example number 1. And we now have 3 tools that we can use to find the response at any given frequency. So if we take a look at this, here we have our actual point-by-point frequency response in black, and I put a little blue dot there that represents our critical frequency, 1592, also the negative 3 dB point, and then our F at 2K comes in at 622 millivolts. And if we were to draw that in a Bode plot, we would take our critical frequency and bring a line directly vertical so it intersects with this horizontal asymptote and use a straight edge on this guy. Pick a second point here, which is a factor of 10 out. So that's a decade out. Put a dot 20 dB down and connect this point with that point, and you have the Bode plot. And Bode plots are asymptotes and they're straight lines. So a decade can mean a factor of 10 or a factor of 0.1, and depending upon what kind of filter we're using, high pass or low pass. And also, if we had, say, a high pass filter, say for example in an FM transmitter, they emphasize the high frequencies, and then what your radio does, an FM radio, is it de-emphasizes them, and everything comes out to be flat as far as frequency response is concerned. So a high-pass filter would actually have a roll up of plus 20 dB per decade. So anytime you're dealing with a single time constant filter, meaning one capacitor and a resistor or one inductor and a resistor, you're always going to be talking about 20 dB per decade, either roll off or roll up, or 6 dB per octave, and an octave is a factor of 2, roll off or roll up. So in the land of high pass, we basically end up doing the same thing, except now we have the capacitor in series, and this guy is going to be in parallel with the output, so we want the voltage drop across the resistor. So in high pass, as the frequencies increase, the value of the capacitive reactance drops, meaning the output's going to rise. And at low frequencies, this approaches an open circuit, meaning the output voltage would be 0 at 0 hertz. So setting this up would be the same as what we did before, and in the numerator we would have Z2, the resistor, and in the denominator we would have the sum total as before. And if we wanted to find the transfer function of this, as we did before, it would simply be V out over V in, again unitless, and then this would be a pure number here with an angle. So it would be handled the same, and you can use any of the 3 techniques that we discussed to figure that out. So let's see here. That'll conclude part 1, and thank you for watching.